Cellular division is the process through which all cells reproduce. It is fundamental for growth, repair of the organism, and reproduction. Even though gametes go through a type of cell division called meiosis, for this project's purpose, I will be focusing on mitosis. Mitosis is the process that all somatic cells go through in order to multiply themselves. This activity makes up a small part of the cell cycle. While Mendel focused on the study of genetics, cytologists made major contributions to the knowledge we now have of cells. It was in 1879 when German biologist Walther Flemming noticed that before cell division, the genetic material inside the nucleus of the cell, which is usually stored in the form of chromatin, condensed and took the form of chromosomes. Every cell in the body stores a person's complete genetic material, yet only a few pieces of this DNA are activated depending on the function of that specific cell. When a cell divides through mitosis, the number of chromosomes remains constant. If a cell has 2 end chromosomes, they will duplicate 4 end chromosomes to then divide into 2 identical daughter cells with 2 end chromosomes each. The cycle continues as is. Taking into account the previously mentioned model of chromosomes in mitosis, I have decided to find a sequence that could perfectly express the number of chromosomes in each generation of daughter cells that come from a specific mother cell. When creating a visual model, it is evident that the number of chromosomes belonging to each generation creates a pattern: 2, 4, 4, 8, 8, 16, 16, 32, 32, and so on. My first task was to create a formula for finding the nth term. The immediate observation that I made was that I had to find a way through which even numbers repeat themselves independently of the number of the iteration. I considered the standard formula of alternating sequences or the behavior of sine or cosine functions to find ways to cancel out numbers, and many other mathematical resources that I have already explored in the past. However, I did not find the answer by going backwards in time. It's crucial to understand that the 2 in the sequence is essentially an outlier since it's the starting cell. After many trials and errors, I decided to look for new and unknown alternatives. I got to know the ceiling function. It is a piecewise step function that rounds a number up to the nearest greater integer. It has an opposite function called the floor function, which essentially rounds up a number to the nearest smaller integer. For the project, I had to adjust the equation in order to let each number repeat itself twice and have the outputs all be even numbers. However, this formula was not exact, since the values of the first and second iteration were 2, and this is not real for my specific case. Taking into consideration that the ceiling function was not exact, I decided to experiment with modules as another alternative to cancel out numbers when the iteration is odd, in order to have the items repeat. In modular arithmetic, a module is the remainder obtained when one integer is divided by another integer. The modulo operation is denoted by the symbol that we use for percentages. For example, if we perform 10 modulo 3, the result is 1. Because 10 divided by 3 is 3 with a remainder of 1. In this case, 3 is called the modulus and 1 is called the residue or the remainder. When it comes to modules, the only possible numbers that you can get from a module are 0 and all the numbers that are below the value of the module. So for example, all the possible numbers for module 4 are 0, 1, 2, and 3. But for module 2, the only possible numbers are 0 and 1. Which were exactly the numbers that I needed to cancel out one number in the odd iterations. I decided to add a small square on the bottom part of the infographic that's called What's Next. What this means is what's going to happen next with this project. I'll be focusing on adding limits. Taking all of the information into account, limits can be applied to this formula considering how many times a cell can undergo mitosis before dying. I will be focusing on cells belonging to the mouth region, for example, taste buds, which regenerate approximately every 10 days. According to some estimates, the turnover rate of cells on the surface of the tongue may be as high as every 3 to 12 days. Assuming an average turnover time of 5 days, this would mean that each tongue cell would undergo approximately 0.2 rounds of mitosis per day. This way, limits can be applied. It is crucial to remember that the purpose of this mathematical procedure is creating a model that allows people to identify chromosomal mutations in any generation of daughter cells to prevent and identify possible diseases. The next step in the project is analyzing limits and continuity. In mathematics, limits are a fundamental concept used to describe what happens to a function or sequence as its input values approach a certain number. It allows us to understand the behavior of functions and analyze their properties. Continuity is a fundamental concept as well that describes the smoothness and unbroken nature of a function over its entire domain. A function is considered continuous if it has no abrupt jumps, holes, or vertical asymptotes. Given the function and table that can be analyzed within my project, it is clear that I am working with a piecewise function, which means it has different intervals and various subdomains. I have created separate equations that represent the trajectory of the chromosomes realistically, which are essentially the steps in my step function. These equations change in every interval and always leave a space between them. To prove that this graph is not continuous through limits, I went through the following procedure. I used the first 5 functions of the intervals of the piecewise function and analyzed their individual continuity as well as the continuity of the entire function. When it comes to the continuity of each interval, I found that every interval is continuous within itself. For example, in the interval 0, 1, where y equals 2 and x is greater than 0 or equal to 0 and smaller or equal than 1, the function is constant, which means that it is continuous over the entire interval. The same happened with the rest of the functions. After doing this, I considered the transition point x equals 1. From the left-hand side of x equals 1, as x approaches 1 from values less than 1, we have that the limit is equal to 2. From the right-hand side, we have that the limit is equal to 4. And since the left-hand limit is not equal to the right-hand limit as x approaches 1, there is a discontinuity at x equals 1. These discontinuities continue to appear in the other following transition points. For example, when x equals 3, 5, and 7, the function experiences a jump or discontinuity. Overall, it can be said that while the function is individually continuous within each interval, it is not continuous over the entire domain. It is clear that the transition points are undefined by only looking at the graph. Furthermore, I added a table where I inserted specific values of x in regards to one of the intervals of the entire graph. This is another commonly used way to identify the limits of a function at a certain point. I chose this interval because of the turnover rate of tongue cells. The frequency of mitosis in tongue cells can vary depending on factors such as the age of the individual, the specific stage of cell differentiation, and the health of the tissue. If we assume a conservative estimate of mitosis occurring once every 48 hours in tongue cells, we can estimate the number of mitotic divisions over a period of 10 days, which is an estimated time of how much a tongue cell can live. The number of mitotic divisions will be 5 over a 10-day period. Based on the data collected, the number of chromosomes stays constant at 8 because of the nature of the function, where it is ultimately a horizontal line between 4 and 5, and as soon as additional decimals are placed to represent a number slightly below 4 or above 5, x will remain undefined. For the final stage of this project, I analyzed derivatives. Derivatives are a fundamental concept in calculus and play a crucial role in various fields such as physics, economics, engineering, and finance. In calculus, a derivative measures the rate at which a quantity changes with respect to another variable. It provides a powerful tool for analyzing and understanding the behavior of functions. In other words, at its core, the derivative captures the instantaneous rate of change of a function at any given point. The topic of my project and the data that I gathered led me to a step function, which is one of the many variations of piecewise functions. This type of function is constituted by merely linear functions without a slope that are continuous within themselves yet discontinuous between each other. Since the derivative of any constant in a function is 0, the intervals in the step function will essentially all have a derivative of 0. However, to make this knowledge applicable to my project, I decided to model a tendency line that gathers all of the data I have regarding the number of chromosomes per generation in cellular division. The tendency line corresponds to an exponential function, where y is equal to 2.4466 times 1.36559 to the power of x. Using this exponential function, I am now able to find a derivative of the function, which allows me to know the instantaneous rate of growth of the number of chromosomes at any given time. To find the derivative of my function, I used the Taylor series, which is better explained in the document that's attached to the infographic. After getting the derivative formula, I recognized that this equation will correspond to the velocity of growth in the number of chromosomes in a certain point. According to the estimation that I made in the limit section, a tongue cell goes through 5 mitotic divisions in a matter of 10 days. This means, according to the equation and Desmos graphs, that at 5 divisions, the rate of growth of the number of chromosomes is equal to 15.22 chromosomes per generation of cells over mitotic divisions, which are the units that I used in my graph. However, this knowledge is way more useful for real-life applications when the graph is analyzed when x represents time. This knowledge is, however, more useful for real-life applications when the graph is analyzed when x represents time. This way, the number of chromosomes per generations of cells over time, or the velocity of growth of the number of chromosomes, can be calculated in any instance. This can be used to track irregularities in mitotic processes.